This paper proposes a new task called zero guidance segmentation, and the first method to solve it. The goal of the task is to segment every object in an input image and label each object in natural language. This is in contrast to traditional segmentation, where object classes must be predefined and are finite in number. The recently introduced open vocabulary segmentation allows the user to segment any objects. However, the user must guide these segmentation algorithms by providing a text query for every single object they wish to segment. In contrast, our task requires no input or guidance from the user to segment all these objects. Our method works by distilling vision language knowledge from CLIP, and solves the task without any segmentation datasets or fine-tuning. Here, we can recognize and precisely locate the Mona Lisa painting, describe a group of people as crowd, and correctly infer the location as museum. Our key contributions are: first, we propose a new task, zero guidance segmentation, and its first baseline which does not require any segmentation datasets or fine-tuning. Second, we introduce a new attention masking technique as part of our pipeline to convert a segment into an embedding in CLIP space with no fine-tuning. Third, we introduce a new evaluation protocol that can utilize existing segmentation benchmarks. Our pipeline starts by clustering pixels based on pixel-wise features derived from Dino, a self-supervised vision transformer, into many small segments. These segments will be converted to embeddings in the CLIP's latent space. Then, the embeddings are used to generate labels for all segments with an off-the-shelf text generation. Finally, small segments that are parts of the same object will be merged together based on the similarity of their segment embeddings and predicted labels. The key challenge in this work is how to embed a segment into CLIP's latent space, which typically takes a whole image as input, not a segment. To solve this, many existing methods simply crop and mask the input image. However, since these masked segments look different from the full images CLIP was trained on, some additional fine-tuning of CLIP on a dataset of masked images is usually required. Nonetheless, masking objects this way removes the surrounding context, which is useful for recognizing this arch structure as a bridge. So instead, we propose to apply masking on some of the attention maps in CLIP's vision transformer encoder. This allows the encoder to focus on the segment, while still preserving the surrounding context and CLIP's original weights. One issue we observed is that while attention masking is effective for salient objects like this cat in the center, it may fail to correctly label less prominent objects like this towel. This can happen because the information related to the most prominent object tends to dominate and become globally present in all patch tokens. To address this, we propose a global subtraction technique, which subtracts the global context, computed from the values of the original unmasked attention, from the masked attention values. The scaling S determines how much global context should be removed and is estimated automatically based on how prominent the segment is. The less prominent the object is, the more we remove. To achieve this, we compute S based on the cosine similarity of the masked and unmasked attention values themselves. This helps balance global and local contexts and bring out more towel in the final embedding. Our method gives reasonable segments, and the predicted labels can describe regions by different kinds of descriptions, such as object names, facial expressions such as grinning faces, locations such as London, car models such as an SUV, or even animal breeds like greyhound. However, quantitatively evaluate these results is not straightforward, because a label can be correctly, but still differ from the test label. Here, greyhound should be evaluated as a segment of the test label, dog. So, we introduce an evaluation protocol using any segmentation dataset. To evaluate a predicted segment, we take its predicted label and find the closet test label by comparing their distance in S-BERT space. Alternatively, we take the segment embedding and map it to the closet test label in CLIP space. Once the label has been remapped, standard metrics like IOU can be used. Even with relabeling, a predicted segment still may be mapped to a test label that is technically correct but does not align with the actual test label. Here, our predicted labels, roof, and pub, are correct, but they are relabeled to the test labels, ceiling, and sign, instead of the annotated test label, building. Here is our qualitative results on segmentation datasets. Our full pipeline have highest scores in most cases. The ablation study shows that using crop and mask often yields incorrect labels. And using only attention masking may label background segment with the salient object. While using attention masking with global subtraction returns correct labels, even for background objects like paved and sky. See more ablation results in our paper. When compared to zero-shot open vocabulary baseline, our method discovers more objects and can offer more fine-grained labels like stool. In a user study, we ask human evaluators to rate how well a predicted labels describe their segments on a scale of 0 to 3. Here are some examples of user study. Our score 3 labels accurately represent their segments, and they can be descriptive, such as sandy beach and crowd observing, unlike traditional labels. Score 2 labels are partially correct. They may fail to describe the whole segment. Score 1 labels are somewhat related to their segments. 0 rated labels are incorrect. From all rated labels, 64% of them are deemed at least partially correct by evaluators. For more details, results, and experiments, please visit our site.